It's with great pleasure to introduce Pierre Cagne, who's going to tell us about parametricity for GADTs. On to you, Pierre.
Thank you very much. So first, thanks for giving me the opportunity to give the talk online. For visa reasons, I can't be in person today, so thanks for that. I'm very grateful. And so today I will be talking about parametricity for GADTs. This is a joint work with Patricia Johann, and this is an early announcement. So that was this special track for MFPS this year. And so I will present something which is still preliminary in some sense. So first, I will talk about what makes a data type the type of data structures in general, before moving to the specific case of GADTs, which stands for Generalized Algebraic Data Types. And so if we view those types through that lens of point one, then we find a problem and we we present a potential solution to it. But this is not fully worked out. So in the third part, I will explain what is still missing and what we still have to do to make everything rigorous. Okay, so in general, what makes a data type a type in which we can find data structures? So to do so, I will rely on examples, not on fully general description of data types. And I will start with list. So side note, all of the code that you will see is written in Agda. It doesn't mean that the meta theory is Agda's type theory. It just means that I need a dependent type theory kind of thing to write my terms. But I will say later in the talk a word about the ambient type theory. So if you have an Agda compiler in your head, some of the things that you will see might not actually type check in Agda. So don't worry about that. Okay, so if we take like one of the most known example of a data type, mainly the polymorphic type of list, then if I take an element L in one of these instance, here the instance at the integer, what I can have as a mental picture for this element is something like that on the right. So I look at the abstract syntax tree of that element, sorry. And I can decompose that tree in two parts, the black part and the orange part. And so you see that the black part is made out of the internal nodes, which are corresponding to the constructors of lists. And the orange part are the leaves. And at the leaves, we find the data that I inputted in my list. So this is very standard. A lot of people have this mental picture when they are thinking of a list. And we can do that for many data types. And so lists is the archetypal example of what we call ADT, so algebraic data type. And so the key feature of those types is that they are recursively defined, but to define an instance, we only need to access lists at the same instance. So you see that the counts constructor, so the second one, takes a list of alpha to give you a list of alpha. But we can move on to slightly more general data types called nested type, like the type of perfect trees that I have written here, P tree. And so this data type has two constructors, leaf and node. Leaf just take a piece of data and give you a P tree, and node construct a new P tree out of an older one. But you can see a key difference with the first example that was list, which is that to define a P tree of type alpha with node, I need a P tree of type alpha cross alpha. So I need to access another instance of the type family to define a P tree of type alpha. So because of that, I need to define the family as a whole and not instance by instance. And I will come back to that point later on, so keep that in mind. But if I have an element of that data type as a specific instance, here n, I can have the same mental picture as before. It's just a little more involved, but I still have a tree in which the internal nodes are the constructors, which are involved in my term P, and the leaves are the data. And so here my internal node contains, well, node, leaf, and also the comma, which is used to define the pairs in the product type. But once I once I write P as a tree completely disconstructed, then at the leaves, I have exactly the data that I inputted in my term. And so you can see that those data have types exactly n, the instance in which I'm looking the P tree family. And the same was true for list. The type of the data of the leaves are exactly the instance that we find here. And I point out this fact because you can see that in those examples, nothing was depending on n. I could have used another type to make my example. I would have had the same little speech about structure versus the leaves in which the data lives. So if I use bool, for example, instead of natural numbers, then by inputting some trues and false in the leaves, I would have had the same exact speech about how to think about data structures. And so that brings me to the most important feature of a type of data structure, which is that the constructor of data structures must be parametric function. They must be uniform in the type that we are handling in some way. And so we can put a lot of meanings behind parametric. We've seen like one way to interpret parametricity, the previous talk. So here, what we mean is, or what we will focus on at least, is relational parametricity a la Reynolds, but externally. So the previous talk was focusing on something internal to type theory. Here we are completely external. Okay. So how to make this statement, this slogan that I just showed precise? So first we need to have like an idea of how to relate data structures, and that is not something new. That's something that has been studied before multiple times. The fundamental idea is that you want data structures to be related when they share the same structures and their data are related. Okay, so what does it mean in practice? So if I have the data type of list as before, how do I realize this fundamental idea? Well, I do that by making the data constructors parametric by definition. And so I do that by just defining a new data type called list hat, list up, that takes a relation as a parameter, and then gives you a new relation between the list at the two instances alpha and beta. And the first constructor, empty at, will just tell us that empty is always related to empty by any lifting of any relation. Yeah, I just said the word lifting. Sometimes I will call list at of R the lifting of R by list. So this constructor empty at just is a witness that this constructor empty is parametric. The same is true for the second constructor. So I make a second constructor const at, which is a witness that const is parametric. So it says like if you have two elements which are related by R and two lists that are related by the lifting of R, then the new lists that you can make with the const are relating by the lifting of R. Okay, this is not something that only works for lists. You see that here I follow a little bit kind of a recipe. I say, okay, for each constructor, I make a new constructor in my new data type, which is a witness of parametricity for my original constructor. So we can do the same with P3. And because in P3 I have leaf and node as constructors, then in P3 hat, I will have leaf hat and node hat as constructors. And each of those constructors will be a witness of parametricity for the corresponding initial constructor. Okay, so that's the fundamental idea behind making a parametric language with data structures such as P3 and list. But now we want to move on to GADTs, which are more general than the data types that we have seen up until now. So I will present a specific GADTs that has enough to expose the problem that we encounter when we want to do the same thing as what we did in point one for GADTs. And then I will explain how to try to find a solution for this problem. So here's my example. I call it lambda because it's supposed to encode some kind of shallow embedding of a small language. And so you see that we have 4 constructors. The first one is very similar to the one that we have seen before. It's construct from alpha, something in lambda alpha. But the second one is already more tricky. It construct out of lambda alpha and lambda beta, something in lambda alpha cross beta. And so that's one of the distinctive feature of GADTs, which is that the constructor might construct elements in a specific instance, not generic instance. So for list and P-trees, we are only yielding things in the instance at alpha of the type family that we are defining. So then by instantiating alpha with everything, with anything, you could construct an element in any of the instance. Here we can only construct elements of the form prod of something in instances which are at a product. And so if I try to mimic the mental picture that I had before for list and P-trees, here I can still do that. I can still produce the abstract syntax tree of my element T that I have as an example here, but there will be differences. So I still have a tree. I still have a tree in which the internal nodes are the constructor of my data type, and my leaves are the data that I inputted in my term. But what you can see is that my term T is of type lambda bool, yet I have some leaves where the type is different from bool, like 1 and 4 are natural numbers. And so somehow there is a mismatch with the type here in bool. So a way to think about that is that this element, true, is kind of a relevant data because it matches the type, but those two are kind of like irrelevant in some sense. That will play a fundamental role because if I replaced 1 and 4 by 3 and 5, basically I wouldn't have done anything to my term T. I will come back to that later, but keep in mind that this is one of the key differences with what we have seen before, is that we still have the same mental picture, but there is this mismatch between the instance that we're looking at and the type of the data that we find at the leaves. Okay, one other thing that I should mention is that in Lambda, because of this specific feature of GADTs, I had to put what was before a parameter as an argument. This is just a very small difference, but it will play a role. Okay, so we still have the same mental picture. We still have something which looks like the declaration of data type. Maybe we should just apply the recipe of before and see what happens. So that's what I did on this slide. I don't want you to just like get what I wrote at once. What I want you to notice, though, is that because of the specific form of prod in my data type lambda, here in prod hat, I produce a result in lambda hat of a product of relation between two elements which are constructed with prod. So I don't have any means to produce an element of lambda hat of R for an arbitrary relation R into between two elements constructed with prod. I can only do that if the relation is a product of relation to begin with. The cross hat is a product of relation. I should have mentioned that. So why do I point that out? Like, what is problematic about that? So I will try to illustrate the problem on an example. So it's basically the same example as before, but you see that I removed like the pi1 and pi2 because I wanted all the data to be relevant in some way. So I have my term U, which is represented by the tree on the left. And then I take another term, which is basically the same with different data, V. So I replace T by F, 1 by 3, and 4 by 5. So if I take a relation that relates T and F, another one that relates 1 and 3, and another one that relates 4 and 5, then by the recipe of the slide before, I can relate U and V by the relation R1 cross R2 cross R3. And it makes sense with the slogan that we had, which is that if you have the same structure and related data, then you should be related as data structures. And there, U and V, by definition, have the same structures. I only mess up with the data, and then I just like suppose that they were related. So U and V should be related as data structure. So this is perfectly fine. But what happens now if I take a relation which is bigger than R1, R2, across R2 cross R3? If I just add a point or 2 points to my relation, what happened and what should happen? So what happened is that U is not related by lambda at R with V because there is no way that R is a product. I mean, it could happen, but here I didn't specify anything, so I don't know that R is a product of relations, so I cannot produce a witness of relation between U and V by lambda hat of R. But should they be related? And there is an argument that says yes, because if I look at my data T14 as a bunch, as a tuple, then it's still related to the tuple F35. So if I look at all my data at once, they are still related by R. So if we follow the principle of data structure should be related when they have the same structure and related data, it would make sense to have U related to V by lambda hat of R. So this is the conceptual reason. On a more technical level, why would we want this R to relate lambda hat of R to relate U and V? Is because when we are trying to make a parametric language, what we want to achieve is usually three theorems. So the very well-known three theorems that has been recalled the previous talk about the identity function, for example. So any function of type 4 alpha goes to alpha must be the polymorphic identity. Here, in the presence of data type, would be something like that. If I have a function which is of type 4 alpha goes to lambda alpha, then everything that I can produce in phi A must be A itself. And then graph lemma is usually also something that you want when you want to marry parametricity with data types. And the graph lemma is something that says that if you have a mapping function, there is two ways of producing a relation out of it. Either you first map a function and then take the graph, or you first take the graph and then you apply the relational lifting to that graph. And you want to find the same thing. And even if for lambda we don't have a fully defined mapping function because it's a GADT and not a nested type, we can still produce a statement that says something along those lines. And so, because we want to have access to those kind of application, the question, the answer to the question of before, let me go back to there, should U and V be related by lambda hat of R, should be yes for just technical purposes. This preservation of inclusion between relation is crucial in those applications. Okay, so we know that the naive recipe didn't work. We tried to do lambda hat, and we noticed that there was this problem with inclusion preservation. And so how can we go around that? And so the technique that we propose is the following. So we just embed the data type that we are looking at, here lambda, into something which is more simple in a way. So there will be more elements, but it will be more simple to handle from the parametricity perspective. So I call this new type lambda C, for the C is for completion, and it's almost a nested type. So then we can apply the recipe, and we know that the recipe will go well because for nested type everything was working correctly. So it will not be exactly a nested type, but it will be close enough, and I will show you how. And then once you have two elements in lambda, and you want to know if they are related by a specific lifting of a relation, the lifting of a specific relation, then you just embed those elements into lambda C, and then you use the lambda C hat, which has been perfectly defined before. Okay, so this is just me recalling the definition of lambda. So how do we make lambda C? So basically, we want to get rid of those instances. I wanted to select that. We want to get rid of those instances where there was a structure in the relation type. So we just want to produce things in lambda of gamma for an arbitrary gamma. So that's what we are trying to do here in the bottom. But we still want to account for the structures that we are getting rid of in the codomain. And to do that, we will just take that into account in the domain of the constructor. So for ink, nothing changed because ink was already good enough for a nested type. So just gamma goes to lambda C gamma. But for prod, now the new prod C, will still take a lambda C of alpha, a lambda C of beta, and it will produce a lambda C of gamma whenever I have a function from alpha cross beta to gamma. And the same is true for the two other constructors. I produce something in lambda C of gamma provided that I have a function where the domain is exactly what was the instant before. Okay, so that's what I call the completion. And why can I embed lambda into lambda C? Well, because if I have an element of lambda, I can just replay all the structure of that element in lambda C by inputting the identity function for each of those extra parameters. So to go from lambda to lambda C, I just put my parameter identity. If I follow the recipe for lambda C now, I find that, which I don't expect you to grasp as one go, but what I want to point out is that now, because of the extra parameter for each of my constructor prod pi1 and pi2, I have also an extra parameter here that relates the function that we now have as parameter in prod C, in pi1c here, and in pi2c here. And so this extra parameter involves the lifting of the arrow, which is translated as follow. Again, that's not anything new. The lifting of the arrow is something which is known for a long time. So we relate to functions by the lifting of S and R, when for every input which are related by S, then the output of, well, F applied to the first output and G applied to the second output are related by R. And so in particular, when F and G are the identity functions, then it really means that S is included in R. Whenever S relates A and B, then R relates A and B. And so for the elements that are coming from lambda itself, that we have inputted in lambda C, then this F and this G will be the identity, as we discussed. And so the missing inclusion that we had before is kind of built in that lifting of the completion now. So we will have the preservation of the inclusion that we discussed earlier by definition, if we are relating elements through lambda C hat. So if you go to the pre-proceeding, we have an example of a free theorem and of a graph lemma, not exactly with that lambda, but a variation of it, using this technique. So we start with a GADTs and we do this completion, and then we look at the lifting of the completion. And so both the statement of the free theorem, the statement of the free theorem, and the statement of the graph lemma doesn't refer at all to the completion. It's something which is completely, standalone, only talk about the GADT, but the technique to prove them go through this completion. Okay, well, good. You could tell me like, well, you have a technique, it seems to meet your goals about free theorem and graph lemmas. Where is the catch? Well, why is that an early announcement and not a fully worked out result? Well, it's because here I just presented you the idea, but if I want to do something rigorous, that's how it would go. What we want to do is that we are looking for a dependent type theory T and a translation from the thing that we want to consider parametric, so system F plus GADT, to that type theory. And so that's why I said that we are talking about external parametricity, because you see that the dependent type theory is a priori much bigger than the thing on the left. Okay, so we want to find such a translation, and so where things are not fully worked out, like what is this type theory? Because this type theory should have some specific properties, and it's not clear how to make all those properties work together. So first, we want T to have an impredicative universe. Because in system F and language with GADTs, everything is impredicative. So if we translate that into a dependent type theory with predicative universes and level of universes, then we will end up with interpretation of GADTs which behave radically differently from their behavior in system F. So we want to have a translation which is honest enough, and so we need to have an impredicative universe for our dependent type theory. We want this impredicative universe to support inductive construction, because GADTs and ADTs and nested type, all the data types that we have seen, come from inductive constructions. And so you could tell me, well, I know such thing, like the universe prop of Coq, for example, is exactly like that. But the universe prop of Coq, for example, is only comprising a proposition. Here we want a universe of proof relevant types, because, for example, for list, we want to be able to distinguish two lists. We don't want two lists to be equal just because they're in the same instance of list. So first, we need that. We need a type theory where there is an impredicative universe of proof-relevant types which support inductive construction. But then we know that impredicativity doesn't work very well with strong sum. And if we have a dependent type theory that needs to be strong enough to make all the translation, probably we would have some kind of sum at some point just to take the total space of type families. And so what is the interplay between the two is not clear for me, because if you just make things too naively, then you just end up with contradictions like type in type. And finally, not finally, sorry, third point, there was a fourth point. The third point is that we need to be able to interpret relation in T, because that's the goal, to make relational parametricity. So a way to do that is to just say, well, relations are families indexed by A and B, which means that we are looking at proof-relevant relations, and they can be a little tricky to handle because we have sometimes multiple witnesses for the same relation. And so, for example, what does it mean that a relation is included in another? Is it enough to just map one of these witnesses to one of the other witnesses? Do we need to map all of them? Do we need to map them injectively? There is a lot of room for interpretation here, and so it's difficult to choose what is the correct interpretation. Of course, we could say, well, if we can't use proof-relevant relations, we can use proof-irrelevant relations, so propositional relation, saying that we are looking at type families indexed by A and B, but only targeting propositions. But then another problem appears, which is that for the graph lemma, which is one of our goals, we need to have graphs as relation, and graphs are based on the identity type. And so if we want the graph of a function to be a relation in the sense of propositional relation, then we need to assume something like axiom K. And axiom K doesn't seem to deal very nicely with non-injective data constructors. And so I will say a word about that, because I alluded to it earlier, but I didn't go in details. That's one of the other key difference for GADTs, which is that data constructor doesn't have to be injective, which is a little bit surprising at first, because for every other data type that you know, ADTs and nested type included, all the data types are injective. But if we want GADT to be data structures in which the constructors are parametric, then we can't ask for injectivity of the data type constructor. So I will focus on pi1 here of my example lambda. If I want this pi1 to be injective, to be parametric, then if it's parametric, beta is not appearing on the codomain. So it means that whatever beta is, it can't have any impact on the outcome of pi1. It would break the uniformity that parametricity is requiring. And so it comes from the fact that I made a little simplification here. I wrote lambda of alpha, but I should really have written lambda of the projection out of alpha and beta on the first component. But if I want that pi1 to be parametric in any sense, pi1 will have to identify some elements. If whatever happens on alpha stays the same, but the thing that happens on beta differ, then applying pi1 to it will just forget about whatever happened on beta, and so I should have the same result. So that's what I meant earlier when I said this 1 and 4 are not really relevant data, in the sense that if I chose other data, I should still end up with the same term in my type theory at the end. And I will stop on that.
Okay. Thank you, Pierre. We have time for 1 or 2 quick questions. Does anyone have a question? I have a question. Your C construction seems a little bit like either Kripke or logical relations of varying-arity kind of thing. Have you seen any connections like that, or is it just me imagining it?
So I'm not familiar with the Kripke construction that you are referring to. What is very similar to for me?
Kind of a future relation, right? Looking at it. Yep.
Yes, in a sense. So Another construction which is really well known, I actually prepared a slide about that here. Another construction which is very well known in that connected to that matter is what we call the sometimes the Henry-Ford encoding of the data type that Conor McBride introduced, where you just say, well, instead of what I did, you put an equality instead of an arrow, because here this lambda f is supposed to really match exactly lambda. And so going from an equality to an arrow, we choose a directionality somehow. And so we say, okay, we will just go to that gamma now, instead of having gamma being equal to whatever was the domain. And so in some sense, yeah, there is a kind of like a, we'll deal with that in the future, because we just wait for the return of that function to produce the elements to the constructor. So I'm not sure exactly of a formal relationship between the two. That might be interesting to look at, but there is something similar.
Okay, I think we better stop because it's the end of the day. So let's thank Pierre again.